Hi, good afternoon. Welcome to our tutorial session. Today we have a tutorial session on integration of prediction and optimization with applications in operations management. And it's my great pleasure to have our speaker, Mengqi, here today. And in fact, this tutorial session will be based on a full chapter written by Mengqi and her co-author, who is also her thesis advisor before she graduated, Max Shen. So I have to say that I think the authors of this tutorial chapter are really experts in integration of prediction and optimization, because they actually chose to, at that time when they got the invitation, they chose to give the presentation as a co-speech at that time, because they say, well, during the COVID, maybe some of them cannot come. Indeed, in the end, Max Shen cannot come due to COVID situation. So anyway, we only have Mengqi here today. So let me just very briefly introduce Mengqi and Max a little bit. So Max is the vice president and pro-vice chancellor, and the chair professor in logistics and supply chain management at the University of Hong Kong now. And that's also why it is difficult for him to travel. She's new in the, just started her career, but very brilliant scholar. And she's just started her career as an assistant professor in operations, technology, and information management at College of Business at Cornell University. So her research interest is about data-driven decision-making with uncertainty in operations management, and she has done a lot of nice work, although I guess, right, although you just started your career, but if you look at the work she has done, it's really impressive. So I'm very happy to have her today here, so let's welcome her.
Thank you, Mabel, for the introduction, and thank you all for joining this session together with me. And it is such a great honor for me to present this tutorial at Informs. And this talk is based on a tutorial chapter with the same title, so you could probably look at that online. And in this tutorial, I'm very excited to let you know how great I think this idea of integrating prediction and optimization in decision making, and what are the possible methods to conduct this idea. So what is the scope of this tutorial? I will start with my motivation for it and explain why jointly considering prediction and optimization might be a good idea. And I will also introduce some preliminary concepts related to this topic as well. And in the second part, I will introduce some representative methods that effectively conduct this idea. In this part, I will focus mostly on the formulation rather than dive deep into the detailed proof techniques. And I will also summarize the high-level ideas behind each method and what theoretical guarantees that one could possibly achieve using each of them. So in the last part of this tutorial, I will talk about applications in operations management using the methodologies that I mentioned in the second part. And in the last part, I will also demonstrate the empirical success and practical impacts of this topic. I also want to add that even though that we try hard, there is so much incredible work regarding this topic, so that there is no way for this tutorial to be complete. It can't completely cover all of the related work. So all we are trying to do here with this tutorial is to provide some starting points to look at for the audience members who are interested in this topic, maybe not very familiar with the details and who would like to explore more. So let's get started with the motivations and preliminaries. First of all, I'd like to show you this figure. it is, I compiled this using data that I put from Google Trends. And I want to use that as an illustration of how people's interest regarding data may be evolving over time. This figure shows the relative Google research frequencies since 2004 of the 3 key phrases related to data: the big data, data analytics, as well as the business analytics. So the y-axis of this figure is the search frequency normalized to 100. So the higher value means that the concept is more popular. And the x-axis is the time frame. So from this plot, we can see that big data is the first one that drew tremendous attention. The popularity of big data, it has a rapid increase after 2010 and hits its peak around 2016. And the term data analytics then become popular after big data draws significant attention, and that describes people's interest in analytical methods. Even after the popularity of big data reached its peak, we can still see from the plot that the interest in data analytics continues to draw significant attention. It is because that data only have value when you know how to look at the information hidden behind it. And that's why the methods of data analytics becomes important. Meanwhile, the key question to the practitioners is that how to use data analytics to derive solid business solutions is the key to practitioners. And this applies to a vast range of industries. And every industry, every company today needs to use data and needs to become data-driven if they want to be competitive in their marketplace. And that's the matrix of business analytics. So business analytics are the analytical methods that focus particularly on business decision outcomes. And as we can see from the plot, this term also take off together with data analytics. So within the paradigm of business analytics, there are 3 different types of analytical methods: descriptive, predictive, and prescriptive. The descriptive analytic answers the question of what happened, and it involves organizing data and then presenting it in a way that it can be easily understood. And it focuses only on what has already happened in the past. It is often used as a starting point, and then it is the most easy to conduct. The predictive analytics instead focuses on predictions, which aim to answer the following question: what will happen? And it focuses on analyzing the past data and try to build models that could anticipate the future. So it is often conducted based on a variety of techniques such as machine learning or statistical modeling. And prescriptive analytics instead focuses more on decision making. It focuses on answering the question of what to do. And this is the most complex stage of business analytics and often requires specialized domain knowledge. So in prescriptive analytics, we seek for decisions that will be the best to take advantage of future opportunities or mitigate the future risk. Therefore, prescriptive analytics, it involves both prediction parts and optimization part. It has the flavor of prediction because it needs to anticipate the future opportunity. It has the flavor of optimization because it wants to find out the best decision regarding to what will happen in the future. So in this talk, we will focus on descriptive data analytics, and we will investigate how to integrate prediction and optimization factors to achieve smarter solutions. To further discuss this topic, we consider this problem setting of decision making under uncertainty, and let's narrow down to the following problem setting. So there will be three key components in this setting. First, there exist random parameters, and let's denote it with y. And it is the source of uncertainty. For example, it can be the stock return, demand, or power usage. And associated with this uncertainty, we often be able to access the contextual information that help us to anticipate the uncertainty. For example, if Elon Musk posts on Twitter, then the price of Bitcoin will probably go very high. And also price will serve as a good predictor of demand, and also the climate significantly affect the power usage. And facing this uncertainty, there are decisions to be made. For example, how do we set the portfolio, and how do we manage our inventory, and how do we schedule the generator within a power system? And all these problem setting can be summarized in this following formulation. We intended to solve this contextual stochastic optimization problem. And in this problem, we restrict our decision into a feasible set S. And the decision maker aims to minimize an objective function C, which depends on the decision that needs to be made and the random parameter y. And the goal is to minimize the conditional expected objective value within the feasible reason S. So the main challenge is that no one knows the distribution of y. Otherwise, this could be easily solved. Therefore, we aim to develop a solution based on data. And the available data often takes the following form, that it includes observations of features and random parameters. So a natural framework is to build a prediction model that anticipates the future and then use the outcome of the prediction as an input to find out the optimal decision. So let's first consider the predictions. The prediction may involve two different types. There are point prediction where we want to find out the value of y given as a function of x. And there are distributional prediction where we want to find out the distribution of y given the feature value of x. And then in the optimization step, given the result of a point prediction, a decision maker may plug it in and solve the following optimization problem instead of the original contextual stochastic optimization. And similarly, if we have a distributional prediction, we can also plug that in and take expectation over that. These are all very straightforward methods. And and very easy to understand. Now let's take a step back and reconsider this two-step predict then optimize framework. In the first step, the prediction models are built to target prediction accuracy. This is often a purely statistical metric. However, in the second step, the final decisions are picked regarding the optimality, which is not the same metric as the accuracy, obviously. And will the misalignment of the targets in these two steps be a problem? Ideally, if we could produce a perfect prediction model, then it should be okay. However, life is not that easy. As the famous quote from George Box, he states, all models are wrong. The prediction is always wrong and it will never be perfect. But it still can be useful to obtain certain decisions because, and we want to investigate in this tutorial that whether and how we can make models more useful if we align the targets within these two steps. So before we dive into the details, I would like to clarify that there are other related streams of work that also focus on decision making and also involves parameter estimation and optimization at the same time. But they adopt very different problem setting compared to the setting that we just introduced. So this includes data-driven sequential decision-making, data-driven distributionally or not distributionally robust optimization, the small data, large-scale optimization, Bayesian optimization, sample average approximation, and operational statistics. All of these topics are beyond the scope of this tutorial, but somehow related at some level. Again, this list is not complete. We only present some representative topics here. And we would also like to refer to these brilliant survey papers for reference regarding relevant topics to our problem setting. Okay, now let's come back to our topic of integrating prediction and optimization, and let's see what are the possible methodologies that effectively conduct this idea in different problem settings. First, let's consider the point prediction. When is a point prediction good enough? Recall that point prediction tries to identify the mapping from the feature X to a point estimator of Y. If there is only a statistic of Y that matters, say, if only the conditional expectation of Y that matters, then point prediction is good enough in such cases. So so in what case, what type of optimization problem that we only need a point prediction? It is when the optimization problem has a linear objective. If the objective function is linear, then taking expectation of the inner product of the decision with the random parameter is equivalent to taking the inner product of the decision and the conditional expectation. So in this case, only this conditional expectation matters. Then our goal is to use a function to learn this mapping from data. And all well-established regression method would do this job. This is a standard way. The most standard way is to adopt regression methods with a mean squared loss, which defined as the following. And asymptotically, under certain conditions, if we have infinitely many data, one would be able to retrieve the true conditional expectation of Y. And you probably noticed that with this mean squared error loss, the optimization goal doesn't play a role in the learning process. And can we do it in a smarter way that taking that into account where we learn from data? So in this seminal paper, Smart Predict Then Optimize, the authors proposed a new loss function takes into account the downstream optimization goal into the loss function. And their loss function SPO is defined in that way. It takes the it calculates the difference between the optimal objective value that one could achieve using a prediction induced by H, which is your hypothesis, minus the optimal objective value if you know the true value of Y. So this, high-levelly speaking, characterizes the excess cost giving an inaccurate prediction among optimal solutions. And then, instead of minimizing the MSE loss, we could minimize the SPO loss in the training process. And there are many theoretical results provided for this loss function. In the original paper, the authors constructed the asymptotic consistency, which states that minimizing the SPO loss will identify the true conditional distribution. Will identify the true conditional expectation. And a later work then provide finite sample performance guarantees in forms of the generalization bound. And a more recent work investigate an extension that considers a blended model that could targeting both prediction accuracy and decision optimality, and the original SPO loss would be a special case in their framework. Now, what if the objective is not linear? In such cases, we need to know the entire conditional distribution to have a better understanding of what will happen in the future. Therefore, we want to predict the conditional distribution as a function of x. And however, there is no well-established standard way of doing it. And in this seminal paper by Bersimus and Carlos, the authors proposed a clever idea that we may assign different weights to each samples that we collected, and that weight can be depend on the value of x. The main idea is that we could emphasize through these weights for more important data samples of the for the given feature value. Then the weighted empirical distribution could be considered as this distributional prediction. Depends on the value of x. So let me give you a simple example. So the beauty of this idea is that multiple machine learning methods can be applied to construct the weights. And let me give you the simple example with a k nearest neighbor when k equals to 3. So suppose that this is the feature space, and it is two-dimensional. And each dot here represents a data collected with a specific feature value. And a different position represents different value of x, and the closer points means that they have similar value of x. Suppose that this dot is our feature value x1, and that is the feature value that is given. And we want to calculate a distributional prediction given that feature, given x1. And so how do we assign weights to the collected data points? So we draw this circle that covers the 3 nearest neighbors, and we assign weights in the following manner. For the data points that is in the circle, we assign 1/3. For the data points that is outside the circle, we assign 0 to their weights. And therefore, if we have a different input feature value, suppose we have this dot x2, and using the same rule, we will have a set of different weights. That's one way of achieving the weights depending on different given feature values. So with the weighted empirical distribution, you could plug it in to solve the original contextual stochastic optimization problem. And there are also theoretical results that one could achieve using this general framework. So in the original paper, the authors analyzed the time and oracle cost efficiency for such a framework, and they also demonstrate that it is asymptotically optimal. In other words, the authors show that optimal objective value and optimal solutions converges to the true ones. And in a more recent follow-up work, the out-of-sample performance guarantee is provided via bootstrap robust approach. So can we construct that weighted empirical distribution using a more integrated method? The more recent paper, Stochastic Optimization Forest, proposed a more integrated method to construct the weights. And note that in the previous slides, the weights are constructed by machine learning models that are trained for the prediction purpose. They are not trained while you training these machine learning models. You only targeting the prediction, and you construct the weights using such machine learning methods, and you use these weights to help you in the optimization stage. So the stochastic optimization forest, instead, they use a more integrated method, and they train a forest to construct weights, but the forest is trained to target the downstream optimization instead of purely prediction goal. And the others overcome the computational difficulty by propose a second-order perturbation analysis to overcome the costly splits, and also they demonstrate the asymptotic consistency similar to the previous work. Now, let's move to a specific setting where the random parameter y is discrete. So in this specific setting, that when there are only finitely possible outcomes of the random parameter, and in this case, the conditional distribution of y could be represented by a finite dimensional vector. And in this vector, each component represents the probability of y taking the corresponding outcome. So in such cases, all we need to learn is to learn the probability vector from data. And the standard approach will be to use the cross-entropy loss, and that is equivalent to maximize the maximum likelihood methods. And in this case, we find the best hypothesis F by minimizing the cross-entropy loss. So can we do it better? In our recent work, the integrated conditional estimation optimization, we propose a better way to learn the probability vector. Instead of minimizing the cross-entropy loss, our framework directly minimizes the downstream optimization goal. We minimize the downstream sample cost induced by the prediction using a hypothesis F. So in the learning process, we find the best F that minimizes the sample cost plus a regularization term. And the sample cost is induced by the decision the optimal decision associated with the prediction that you could achieve with F and the sample of feature X. Notice that here we need to calculate this argmean. We need to calculate the optimal decision induced by a given probability vector. But as long as this problem is convex, it's not hard to have an oracle that help us achieve this goal. So the main computational challenge here is that the optimal solution mapping, recall that this is a mapping that we take an probability vector as input and we output in an optimal decision. This mapping is not differentiable and it is poorly shaped. So this figure is an intuitive illustration of the shape of this optimal solution mapping. And as we can see, it has this piecewise constant shape. So it is not differentiable. The high-level reason of why it has this piecewise constant shape is that you may consider a linear programming over a polyhedron. So when you have an objective, one of your optimal decisions should lie in one of the extreme points, and you change your objective a little bit, you stay in the same extreme points, and you change your objective more, and you may suddenly jump to a different extreme points. That's the high-level idea of why this piecewise constant shape appears. And to address this difficulty, we approximate it using a differentiable function, and we can still achieve performance bounds, which is good. And so the main results in our work, we demonstrate that this framework that we proposed is asymptotically consistent. To be more specific, it can successfully recover optimal objective value, optimal solutions, and the true probability distribution. And we also provide out-of-sample performance guarantees in the form of generalization bound. Okay, so another natural idea of integrating prediction and optimization is to directly learn the feature to decision mapping. And there are multiple attempts to explore in this direction. Notice that the challenge of feasibility and the non-differentiability still remains, so that it is still difficult to construct reliable solutions. One way of learning this feature to decision mapping is to use the reproducing kernel Hilbert spaces. And there is a recent work that mostly focuses on unconstrained cases. When there exist constraints, the authors handle it with a penalty term. They also provide performance guarantee, but the performance guarantee also depends on the coefficient of the penalty, which could be large if we intend to force the feasibility. And another trend is to learn this mapping using a neural network. So to overcome the non-differentiability, there are multiple attempts in the existing literature. One method is to approximate the gradient by solving a group of linear equations based on the KKT condition. And the other one is a highly practical one that provides a differentiable optimization layer that is very easy to implement with CVXPY, the existing Python library. And another work proposed a neural network structure that handles feasibility using projection. And one of our recent work avoid this non-differentiability and decides to relabel the data set with a surrogate optimal decisions, and we directly build a supervised learning framework upon that. Again, this list does not cover all related work. These are also many interesting studies for graph-based setting and combinatorial problems, which is beyond the scope of this talk. And so most methods listed on this page do not provide sound theoretical performance guarantees, but they have their own advantage of being highly practical, easy to implement, and scalable. In the remainder of this talk, I would like to dive deeper into the applications, and I will start with more details about our recent work, which is the last one on the previous slide, and I'd like to use it as an example to show the practical impact that one could achieve with this high-level idea. And let's get started. So let me start with a real problem faced by JD.com. JD.com is one of the largest online retailers in China, and it has been growing rapidly in recent years. And it stands out from its peers with its high level of customer satisfaction and its guaranteed fast delivery. So to achieve this, so JD.com has guaranteed the same and sub-same day delivery for more than 90% of the orders. And to achieve this fast delivery speed, inventory management is the critical part. The key point is that we place the inventory at the right place that is close to customers before he or she orders. Of course, it is not easy. There are many challenges. The demand and vendor lead time are both random, so we are facing multiple sources of uncertainty. And it is a multi-period setting, so it is not a one-shot decision. And the JD.com has to handle hundreds of thousands of SKUs simultaneously, so that it must be automatic and scalable. And also the data has a highly time series nature. Fortunately, we have a lot of data to use. So let's look at the replenishment problem. Our decision is the order quantity that one would place to the supplier. And the basic trade-off is that we want to minimize we don't want to be overstock because that will give us holding costs. And we also don't want to be understock because that will give us a back order cost. So we're trying to decide how much we should order at each ordering time. So this is a classic problem from the textbook of supply chain management or the classroom of supply chain management. All of us know that the optimal policy structure is a state-dependent base stock policy. But the problem is that how is the optimal base stock level depends on the state. So do we want to assume that the demand is IID depending on future? Do we want to assume that demand is IID following a normal distribution? Of course not, because there are various demand patterns emerged, and from this plot we can see that the demand is definitely not IID. So we need a more automatic solution that is scalable and handles time series data, and it is a must-have for JD.com. So at JD.com, there used to be a forecasting team that built models that takes data as input and output demand prediction. And there is also an algorithm team that develop inventory algorithms that use the predictions as input and output the replenishment decisions. So in this work, we aim to provide a solution that takes input data and directly output the replenishment decision. And this is our so-called end-to-end model. So to build such a framework, we need two components. First, we need a training data set. The training data set, it has better to be many pairs of features and the right order quantity. So to get the features, it is easy. The features we could obtain from previous observations of demand and vendor lead time, and we can also use the contextual information. But how do we get the right order quantity is a question. We don't want to use historical order quantity because that makes no sense, and it should be the right answer for the reordering problem. So what we do in this work is to look backwards. The optimal order quantity of a past order is not given, but we can always look back because we already know what happened after that order has been placed. So we always look back and see what we should have done at that time in the past, and we derive the best ordering decision given the realized demand and VLT. So in the second part, we want a reliable, we want a powerful enough model that could potentially fit this very complicated mapping between feature and the output decision. And we propose a two-module neural network structure that helps us achieve this goal. For the sake of time, I won't be able to dive deep into the network structure. So I want to pause here to see whether there are questions regarding this part, also the previous part of methodologies.
Question. You mentioned moving from the non-differential space to the differential space. Mm-hmm. But so what did you use to do that? I mean, a transformation, or what was the process?
You mean this part when we approximate this non-differential shape using differential shape? So, so the way we achieve that is that because we want to approximate this optimal solution mapping, and what we do is that, and we have the access to the oracle that we give a input probability vector to the oracle. The oracle gives us a associated optimal solution, and we want to approximate this input and this input probability and the output decision, right? And so we call the oracle multiple times. We randomly throw in the probability vector. We sample the probability vector over the simplex. We have a data set of input of P, the input probability vector. And we call the oracle for each of the sample, so that for each sample we will have an associated optimization. That is the precise output of oracle. So we collect all these data samples, and we could use interpolation to approximate this mapping. We could use differentiable function like polynomial function to interpolate this mapping. And that is when the oracle doesn't have noise. If the oracle does have noise, we train another regression model upon it using differentiable functions. So in either way, we will achieve a differentiable mapping that closely approximates the non-differentiable shape. And we use that in our proposed framework in the learning process. Does this answer your question?
Yeah, so does that introduce any additional error function?
Yes, that indeed introduce approximation error, but fortunately we have performance bound on that error, and we could still achieve the finite sample performance bound and the asymptotic consistency even with this approximation error. It will introduce additional terms, but we could still bound it.
Okay, thanks.
Yes.
Thank you. On the last slide that you were just on, where you're generating your, I guess, your truth data?
Is it this slide?
Or maybe it's not the last one. The one with the
This
yes,
one?
that one. Simple question. What do you do when you stock out? Like, how do you figure out the right order quantity when in the historical data you actually ran out of stuff? How do you know how much you should have ordered?
Yeah, that is a great question. So I didn't mention that in our problem setting, we assume fully stock out. So,
speak to the microphone.
Okay.
We're recording.
Okay, yeah. So this is a great question. So I didn't mention that in this problem setting, we adopt a fully back order where we calculating the label here. So yeah, so it is fully back ordered.
Maybe I didn't understand what you were doing, or I didn't ask my question right. So my understanding was you looked historically, and whereas before you ordered, your inventory was high, and you calculated as if you were going to stock out, right? To figure out, okay, well, if we had perfect knowledge, we would have ordered X, so that when X arrived, we had 0 on the shelf.
Yep.
Okay.
Yep.
And so what if your historical data, in truth, you actually did have 0 on the shelf, but you had extra orders waiting? Does that make sense? So when you're calculating, if I had perfect...
I don't think I understand your question. What do you mean by extra order waiting?
So if you go back to the previous slide that looked like this?
This one?
No, keep going multiple.
Like this one?
Yes. So my understanding was you basically dropped that down so that when the orders came,
we
you were at 0.
calculate the exact amount that gives you like no excess inventory, but also no back order.
Right. So I'm wondering, what if historically you actually ran out before the replenishment came? How do you handle that?
So, if I understand your question correctly, are you do you mean the issue of sensor demand because you already backed ordered, you can't see you can't have the demand will be censored? Is that the issue?
Yes, I think so. Yeah.
Yeah, so for sensor the demand, that is also a great question. For sensor demand, in this specific model, we do not address that issue. But at JD.com, they have a standard pre-processing step that try to recover the true demand from the sales data. Yep. So we use the pre-processed data set, and we believe that is true.
So thank you so much for the really intuitive and well-presented talk and tutorial. My question will be, so recently there is a paper for linear optimization, contextual linear optimization. The authors, I think Hu et al., said that it is better to use the weighted SAA, the weighted sample average approximation, over the SPO for linear optimization. But how about if it's not linear? Should we still use weighted SAA over ICEO, or we should use ICEO over weighted SAA? But I think is there like a framework on like, in linear world we should do, it's recommended to use weighted SAA. In non-linear world, we should do something else. Like, I think, is there a framework yet to use so that practitioners can use in their optimization? Now, I have another question. So there's another divide. So that, I hope. So the first one is like, what is that one, and the other one is there's also. Okay, yeah. Thank you. Yeah, thank you, Manga. Go ahead.
Yeah. So thank you for the question, and it is a very good question, and. So from my intuition, the nonlinear space doesn't necessarily replicate what happens with the linear objective. And regarding to this, oops, yeah, from my intuition, what happens with nonlinear objective doesn't necessarily replicate what happens with linear objective, but for the specific paper and the two methods that you were talking about, how does corresponding methods, how does the weighted SAA compare to ICO when the objective function is linear? That is a really interesting research question, and I haven't investigated that, but I'm very happy to talk more about it offline.
I think, thank you. The second question is, there's another battle like some proponents prefer, like, I think DRO is better than combining integrating optimization and prediction, which is usually called contextual or conditional stochastic optimization. But the other way around is also mentioned by some other authors. Like, what is your opinion about this, like, war between the ROs and the stochastic optimizers?
Okay, this is a very, I have the feeling that, yeah, this is a very broad question. And to answer this probably, we're opening a very long conversation. And is it okay if,
We can
because,
move on.
yeah,
we can
for
move
the
on
sake
later.
of
Yeah,
time,
thank you.
we could we could discuss it like at the end of this presentation, if you don't mind. But this is a great question. Yeah.
Thank you. We have many scholars in different areas over here, so I guess later on all of you can discuss more about this. Any other questions from the audience at the moment? You have one? Did you raise your hand? Oh, okay. All right, yeah. Please carry on.
Okay, so I'll continue with the empirical success and practical impact that we achieved using the previously mentioned end-to-end model. So with the model that I mentioned earlier, we conduct a series of numerical experiments at JD.com. First, we conduct a thorough offline experiments, and we compare with multiple benchmarks, including an end-to-end model without deep learning, because we want to see how powerful our two-module neural network will perform. And we also consider the two-step model that use the same neural network structure for the prediction. And then we plug that prediction into optimization stage. So to compare with the two-step predict then optimize framework with the same neural network, we see the benefits from both the idea of end-to-end of integrating prediction and optimization and the power of deep learning. Then we implement this model at JD.com, and we conduct a field experiment starting from March to April on 2020. And in that field experiment, it involves 12 distribution centers, over 9,000 SKUs, and the benchmark is JD.com's original two-step framework. And from the result, we could see that it significantly reduces all of the metrics, including holding cost, stock out cost, and the turnover rates and the stock out rates. And we also conduct analysis to address the potential selection bias, because the control group and the treatment groups are not 100% randomly selected, but I won't waste time on all these details. Now, this method is currently being used at JD.com, and it is currently serving over 9,000 SKUs. And it has also been shortlisted for the top 6 of the Gartner Power of the Professional Supply Chain Award. So that's, I'm very proud of it. And besides the aforementioned work, there are also other applications in supply chain management. So again, on this page, we restrict our scope to the application of such methods that using methods that are introduced previously in this tutorial. For inventory management, there are multi-product news vendor. This example has been considered by multiple papers that previously mentioned in this talk, and there are multi-warehouse news vendor problem, and there are also multi-period replenishment, which considers by our work and the other work of Dante et al. And the capacity planning problem is also another user case of the integrated prediction and optimization methods in supply chain management. So there, in one of the recent paper, the authors consider a practical two-stage capacity planning problem. And also in another paper that has been posted last year. The authors considered the last mile delivery problem and how the decision maker should assign delivery task to the vehicles and how to determine the sequence of the task. And they tried this smart, predict, and optimize framework on this applications, on this specific application, and achieve very good results. And there are some other applications in operations management besides supply chain. For example, in the portfolio optimization, where the decision maker aims to find the most profitable assortment of assets facing a random market, there are multiple criteria being considered in the literature. For example, the mean variance portfolio optimization, and there are also variance-only portfolio, and some literature consider the conditional value at risk of the return given as of the assortment of assets, and etc. And in power system operations, some recent work investigate grid generation scheduling, some consider the network constraint unit commitment, generation dispatch problem, and the reservation schedules. And a recent work consider a renewable energies trading problems. And the earlier work consider a battery storage optimizations. So these are a summary of the applications that we could find in operations management. Again, there might be other incredible works under this tree. So as we can see, it is an interesting topic and a very exciting research area. And from my opinion, it calls for innovative methodologies to model it and solve for such problems. And it also strikes for a balance between analytics and practical applications. So that is all I want to share regarding this topic. And thank you all for your time and attention. And I hope that this may help your next data-driven project.
Thank you, Mo, for a great talk. I think we have some questions here.
Yep.
So I was just wondering, what were the features you were using in your model?
Which one?
The neural network.
Okay, you mean the features here?
I think it's the next slide, maybe.
This here?
Yes, yes.
Yeah, so the features are, so we obtain these features from our historical data set, and we, using past historical demand, we also have statistics of past historical demand, and we consider like different time series type of features regarding demand. And also we do the similar thing for the vendor lead time. And we also have some contextual information, like some side informations. We have the price of the product at that time, and we have the whether there are promotions where there will be a big selling season like the Black Friday type of promotions. So we have all this information included in the feature. So it's a very, it is a huge set of features. So hope that answers your question.
Hi, so first of all, thank you for this great presentation. My question is also related to this slide. So you mentioned that in order to train this end-to-end model to ask the neural networks to approximate the optimal solution provided by the oracle. And sometimes if the oracle optimization problem is too complicated, if the feasible region of the oracle problem is too complicated, then the output neural network could induce infeasibility. So do you add this as a additional explicit penalty to the end-to-end neural network, or how do you deal with this infeasibility issue?
This is a very great question. So, so in this end-to-end model that I'm presenting here, there is not much constraints on the decisions because we're considering this single item, single location, multi-period replenishment problem. So it is not a big problem here, but as I mentioned earlier, if this is what you just mentioned, is the #1 challenge if we want to learn the feature to decision mapping. And there are multiple attempts in literature that try to overcome this mapping, and I've summarized it on this slides. So there are multiple ways.
Does this method require a lot of historical data?
The one that we collaborated with JD.com?
Yeah, the end-to-end. Because could you do it with small data sets, or does it have to be larger data sets?
It requires large data sets. Super large, like 40,000, something like that. Yeah.
Any other questions from the audience? I guess for the benefits of those beginners who may, be interested to work in this area in the future, can you maybe point them to a few, references that they should start with? I know we have this full chapter that you have written up with Max, but I guess maybe you can just emphasize a few most important references that people may start with.
Yeah, so for the most important references or for the must-read papers, I would say the papers that I have in the methodologies part. So it's so I would say the Smart Predict and Optimize, and this seminal paper of Bersimas and Carlos called From Predictive to Prescriptive Analytics. And I would say our paper would also be a good reference as well. And for sure, at the very end,
I'm waiting for you to say that.
And for sure, at the very end, like all of these are included in our tutorial chapter. So that may be your starting point for this topic. Yeah.
All right. Thank you very much. And any other questions from the audience? All right. If not, thank you very much for being here.